Welcome to physics. Today we are continuing on with our practice really with solving for distance using the linear equation. And again, we're looking at problems that have a constant velocity. So with our first activity, we looked at the relationship between distance and time. And then we determined that that was a linear pattern in the sense that when you have the two data points coming together at a constant velocity, then the data will create a straight line. And that is the pattern that we're seeing. And therefore, we can use the linear equation to solve for it. But then again, at the very end of the last assignment, I asked us to rewrite it. And so this is really the equation that we're going to be using, but hopefully you can see how it's the same. So instead of distance, or sorry, instead of y, it's distance. Instead of m, we have velocity. Uh, Instead of x, we have time. And then our b value would be our starting distance. And that's if we are starting not from, zero, if you will. So uh, that's just a little bit of a recap on how we're continuing on from our last activity. And to help us with that as well, I have a slideshow just to, again, refresh back to our previous activities. So if I go through this just briefly, again, this is what we first introduced, y equals mx plus b. Hopefully this looks somewhat familiar from math. But then in science, right, we can change what those actually represent to make it mean something, right? It's not just a variable, but now it means something in the real world. So with that, if we are focusing on solving for distance, then that means the scenario or the problem that you're trying to solve is going to provide the time, velocity, and potentially the starting distance. And I say here, starting distance or assume zero. If the word problem, if the problem scenario that we're trying to solve here in physics doesn't state, started 10 meters away, didn't, 100 meters away, that kind of thing, as far as like starting distance or starting point, then you are going to assume zero. Okay. And basically that means we're calculating the distance from wherever it started to where it's ended. So that's why we can assume zero there. So then again, one way to rewrite this, just with the variables labeled, with when you see t, that's going to represent time. V is going to represent velocity. Our total distance, again, so that's really, when we're saying solve for distance, that's the total distance of the scenario. And so that will just be d. And then starting distance, we have labeled here as di, and really what that's saying is your initial distance, right? So what was the starting point? So distance initial. If I wanted to be more technical, we could label this distance total and then distance initial. But I thought this would simplify it a little bit, especially since most of our scenarios won't have the di. Okay. But it's important to know that it's there in case you see it. So going through an example real quick, hopefully we feel comfortable plugging in the numbers and how to plug that in. So we have distance equals VT plus DI. And in the scenario, I'm just giving you the numbers, right? So, what is the distance if you're traveling for 200 seconds at 1.5 meters per second? And we don't know the starting distance. So starting distance will be zero. So then again, with velocity, 1.5 times 200, that's going to give me an answer of 300. So my distance is 300 meters. Now, a little bit of a word problem. Okay, so Diego watches a thunderstorm from his window. He sees the flash of a lightning bolt and begins counting the seconds until he hears the clap of thunder 10 seconds later. Assume the speed of sound is 340 meters per second. How far away was the lightning bolt? So we know that the speed of light is much faster than the speed of sound. So Diego saw the lightning and then took 10 seconds to hear the thunder. So then how uh, far away was the lightning bolt? So we can then calculate that. We have a velocity of 340 meters per second. That is the speed of sound, rounded a little bit, but for our sake, the speed of sound times 10 seconds. So that means the lightning bolt was 3,400 meters away. And again, please use a calculator if you need to. There absolutely is no reason why you shouldn't be doing that. And that's it. So really, I want us to focus on just this. So we're practicing getting the velocity and time together to solve for distance. So I have a couple problems here for you where I just give you the numbers. And I also want to get us in the habit of using our units. Okay, so all of these distances are going to be either meters or kilometers, I believe. So the one thing with these equations, our velocity is going to give us the units for both time and for distance. So if it's a meter per second, that means our distance answer is going to be in meters. Okay, so that's really important. So again, we have this. I do want you to show your work. So if you click show your work, you can type your problem. And I would love to see you type the equation first. Okay, and then as you enter the numbers, you can represent it like that, and then get your answer. Okay, then you would want to convert it over here. So you can write it out or just do an M for meters, and there you go. So again, same thing. Now here, okay, again, when we're looking at our velocity is meters per second, and I give you the time in minutes, then you have to do a little conversion. You have to convert the 2 minutes into seconds so that these match. Otherwise, this equation is not going to work for us. Okay. Then again, I mentioned kilometers or meters. This velocity is kilometers per hour, and this is even though we haven't really utilized it much so far. This is pretty common, right? Similar to how here in the United States we use miles per hour, every other country uses kilometers per hour. So it's a much larger distance. And so 60 kilometers per hour, I'm pretty sure is closer to like 30 to 40 miles per hour. So that's a relatively common speed that you might be traveling in a vehicle for 2 hours of time. Okay, so keeping that in mind. Okay, again, trying to trick you a little bit. This is kilometers per hour, but I've given you minutes. So can you convert 30 minutes into hours? This one, we have a starting distance, so make sure you're paying attention to that. And then we have a few word problems. So similar to the example, the information you need is in the word problem. You have to pull it out and put it into the equation properly. And then there's also some tricks to this because these are relatively realistic. And so when you're doing this, I want you to think about what it says very closely. And if it helps you to draw it out, then please do so. So this problem, I'll kind of help us through it. During the Apollo moon landing, reflection panels were placed on the moon. This allowed Earth-based astronomers to shoot laser beams at the moon's surface to determine its distance from Earth. Right? So here on Earth, they shoot a laser beam and they want it to bounce back and get back to Earth. The reflected laser beam was observed 2.52 seconds after the laser pulse was sent. So if the speed of light is, and again, this is a little rounded, but 300 million meters per second, or 3 times 10 to the 8th meters per second, what was the distance between the Earth and the Moon? So again, I'm not going to solve it for us, but you want to start with distance equals velocity times time. Okay, and if you prefer, maybe like that. Okay, so then the trick for this problem, okay, our velocity, I wrote it out for you. So it might be easier in your calculator to type it out like that. Okay, so there's our velocity. And technically, I should write meters per second. And now you're trying to multiply it by the time. And the time that it gives you is 2.52. But what I want you to think about in this scenario and what I'm going to draw for you, I'll do a different color. Okay, we have, scribble. I need to scribble. There we go. We have the Earth, and then we have the Moon, and we're shooting a laser beam, so let's make that orange and dashed. So we're shooting a laser beam to the Moon. Okay, and then it's reflecting back to the same spot, really. Okay, like that. And that whole process took 2.52 seconds. So you really need to divide that by 2, by half, to solve what is the distance to the Moon. If you just use 2.52, you're actually solving what is the distance to the Moon and back. So keep that in mind as you complete this equation up there. Then very, very similar problem. Again, real life example of how you could determine the depth of the Grand Canyon. So Cameron stands at the rim of the Grand Canyon and yodels down to the bottom. He hears his yodel echo back from the canyon floor 10.4 seconds later. Assume that the speed of sound, similar to before, is 340 meters per second. How deep is the canyon at this location? So again, if I were to draw you a little picture, we have, I don't need a dotted line anymore. We have this Grand Canyon, way deep, and then there's the bottom of the canyon. And at the top here, we've got a little person yelling down. Those are sound waves. Okay, yelling down. And the timing for it to get there and back, again, it says 10.4 to get down and back to the ear at 340 meters per second. So you really want to make sure when you're thinking about the timing that you divide that in half. Okay? And that's it. And again, hopefully this will help us feel confident about solving for distance. And then we're going to be rearranging. So we haven't rearranged this equation yet, but next time we're going to be solving for velocity and solving for time. So, well, solving for time and then solving for velocity. And so that requires that we move some of these around in order to isolate time. So that's it though. Right now, we don't need to rearrange the equation. We just need to practice using it. And so we feel confident. And please let me know if you have questions, and good luck.